Hello and welcome everyone to this 1W-Minds seminar. Today's speaker is Daniel Herbst. He's a PhD student at the Technical University of Munich. And today he's going to talk about transferability of graph neural networks beyond message passing. Please.
Okay, thank you very much for the introduction and also for the invitation. It's a pleasure to be here. Today's topic will be the transferability of graph neural networks beyond message passing, and this is based on a joint recent work together with my advisor, Stephanie Egelka. Let me start off by explaining some motivation of the goal we're trying to achieve here. So in graph machine learning, we typically aim to make predictions about graph structured data. So think of molecules or a social network or things like that. And so we have these graphs here as inputs to our neural network, which we call graph neural network or a GNN. And in this case, we just say we make graph level predictions. So for example, a real number. And transferability means that, say, we might have trained a GNN on graphs of a certain node size, but we want them to generalize to larger ones. One can consider kind of this notion of extrapolation. Well, one would look at arbitrary graph topologies, but this is very difficult and usually requires very specific assumptions and some like algorithmic alignment. What we do here is we ask if we can say more when we assume structural similarity between the graphs that we want the model to generalize to. And in this case, it's common in the literature to look at graphs that are derived from, for example, the same graph limit object. So derived means they are, for example, sampled from some random graph model or discretized. And in this work, we look at graphons, which are dense graph limits, as they are in some way nicer than sparse graph limits, as they admit like nice mathematical tools. And the idea is that we have our finite graphs here, and we embed them into the space of all graph limits. And in this space, we have a metric structure, and these distances in this space would reflect structural differences between the graphs. And our original GNN will also be lifted to a function on the graph limit space. And then we would want things like, okay, if graphs are structurally similar, then the GNN will also output similar predictions for them. And so in the standard case, one would say, okay, we have a graphon here, for example, we would sample two graphs from them. And we would say, okay, if the sampled graph is close to the graphon, then we can just invoke the triangle inequality to say that the two finite graphs are also similar. So in previous works, this has been thoroughly studied for message passing GNNs, which is somewhat the most common paradigm in graph machine learning. However, this has some limitations in expressive power. And what we're looking at in this work is what can we say about transferability for more expressive architectures. The structure of this talk will align with the diagram I just showed on the previous slide. So we will start with some background on the types of GNNs we will look at. Then we will introduce the space of graph limits we operate in, the graphon signal space. And then we will lift these models to the graphon signal space and finally study convergence and transferability in them. So maybe just let's briefly review the most common paradigm in graph learning, which are message passing GNNs or MPNNs. And the way these work is you are given some graph and you have node features, which we denote by X, and you can also represent the structure of the graph by its adjacency matrix. And then you initialize node embeddings and you iteratively update them via neighborhood aggregation. So you basically have some aggregation function here over like this multi-set, which could be a sum or something like that. And then individual components that would be acting on, for example, these node embeddings would just be implemented by MLPs. And you do this a couple of times, and then you end up with like some learned node embeddings. And to obtain a graph level prediction, you would just use a readout function. And the important thing about like kind of this modeling is that, well, the output here is independent of the specific ordering of the nodes that we would have. So if we can order the nodes any way we want and look at the adjacency matrix, but well, this output would be invariant with respect to the diagonal action of the symmetric group, basically. So just like one example are graph isomorphism networks, where you basically, so you just apply the adjacency matrix or like the shift operator to node embeddings and then apply some nonlinear function and you iterate these things. The expressive power of these MPNNs is, however, limited by the one-dimensional Weisfeiler-Leman test for graph isomorphism. And this is not very surprising if you look at the iteration here. So you also just like produce a coloring of the nodes, an iterative one, where you start with the node features, and then you just perform also this neighborhood aggregation. And after some finite number of steps, this has to stabilize, and then you just output the multi-set of colors. So as I already mentioned, the expressivity of MPNNs is bounded by this graph isomorphism test. So in the sense that an MPNN can also not distinguish any, well, two graphs that are not distinguishable by this graph isomorphism test. So this is, for example, well, very popular, well, kind of pair of graphs that are not distinguishable by 1WL. Motivated by this limited expressive power, one can also look at higher dimensional extensions of this graph isomorphism tests, which are the k-dimensional Weisfeiler-Leman tests. And the idea is basically that instead of operating just on the nodes, you now operate on k-tuples of nodes. And the way this works is you, well, start with an initialization of like the coloring as well. And instead of just initializing it with the node features, you have to initialize like a k by k matrix for each node tuple, where you would write just the node features on the diagonal and the somewhat like local connectivity structure of the tuple on the off diagonal. And then you would also prefer an update, however, now for each tuple. So in this case, we would have k equals 3. We would just perform k aggregations over different slices of like all these tensors we have. So in this case, over like 3 slices where we just look at, well, the slice where we would, well, have all tuples here that would share one coordinate with the original one. And we would then finally also just output a multi-set of colors, and well, as soon as the stable partition is achieved. And there is like this naive KWL test, but there's also the folklore KWL test that is a lot used in practice, where you just simply, well, change the order of the multi-set and the vector here. And this actually gives a greater expressive power. However, as like the standard KWL test is a bit easier to analyze in our setting, we will stick with that. However, all results would generalize easily to the FWL. As for more expressive GNNs, one very old and popular idea that has been around for a while now are invariant graph networks. So this was originally proposed by Moron et al. In 2019. And the idea is to process, well, these graphs through linear higher order tensor operations, which maintain permutation equivariance. And the building blocks of these IGNs are these linear equivariant layers. So basically, you take all linear operators operating on these tensors here, so from a K tensor to an L tensor, which are equivariant with respect to the diagonal action of the symmetric group. And it is pretty straightforward to show that the dimension of this space is just the K plus L Bell number. So this also has a connection to the partition algebra. Just recall the Bell number is just the number of partitions of a finite set. And what is interesting about this is that one can actually find a basis of this space that consists of very simple operations, like just the identity or basically summing over a row and replicating like certain columns. So, I mean, in this case, it's just for a 2-to-2 tensors, but you see these are all like very simple basic operations. And this means you could also apply, so you could parameterize a GNN via basically the spaces here and apply it to graphs of different sizes. And the way that you would construct an expressive GNN out of this is you use these linear equivariant layers as building blocks and build some kind of like an MLP out of it, where instead of, well, for like the computational graph, instead of considering a single weight, you just consider like some linear equivariant layer. So you start with the graph, which you represent as like the adjacency matrix and your node features, and then you just like produce basically, well, this output here via these tensor operations. And it has been shown that if you, well, have unbounded orders, then you can achieve universal approximation on graphs up to a certain size. And if you restrict the tensor orders up to order k, then you're KWL expressive. There are other higher order GNNs that align with the KWL test that are also directly inspired by them. So, for example, in this case, you would just, like, if you look back at the coloring that is produced by the KWL test, the update here is very similar in the sense that just like the, well, the multiset operation is replaced by some aggregation function, and the specific parts are just like MLPs. And these are all KWL expressive. Okay, so to gain a finer grained notion of expressivity, what can be very helpful is the notion of counting some certain substructures, or in this case, homomorphisms. Just recall very quickly, a homomorphism from a graph F to a graph G is just a function of their nodes that preserves the graph structure and also the node features. So it's also compatible with that. And many graph parameters are actually directly expressible as homomorphism counts. So if you take the homomorphism counts of star graphs into some certain target graph, you get moments of the degree sequence. And if you take homomorphisms from a circle into the target graph, you get moments of the well, spectrum of the of your shift operator. And by a famous and old theorem of Lovash, two graphs G and H are actually isomorphic if and only if the homomorphism counts with respect to all pattern graphs coincide. And for 1WL, for example, there is also a simple, well, characterization in terms of homomorphism expressivity, namely then that the homomorphisms are the same for all pattern trees. For KWL, there exists a similar expressivity result, which is based on the tree decomposition. So the tree decomposition, basically you start with, for a graph, you start with a graph and you build a tree out of bags of nodes. And the tree has to be of the form that basically each edge has to occur in one bag of this tree here. And the occurrences of the nodes have to be connected within the tree. And well, the tree width would be then the mini-max bag size of such a tree decomposition that you could find for a specific graph. And in some way, this is a measure of how tree-like a graph is, in the sense that an algorithm could process it in the same way as a tree. And the basic result here is that two graphs G and H are K plus 1WL or KFWL indistinguishable if and only if these homomorphism counts are the same with respect to all graphs of tree width bounded by K. Okay, so we've now seen these discrete higher order GNNs and IGNs that are more expressive than MPNNs, and we've seen them in the discrete case, but yeah, what we'd now like to shed light on is this graph limit space that we will actually operate in. So maybe let's quickly introduce graphons. So formally, a graphon is just a well, bounded measurable function on the unit square. And this could be intuitively seen as just an infinite extension of the adjacency matrix of a graph. So you just like the node set of the graph would just be the unit interval. And well, instead of a graphon where the values are in the unit interval, you could also just consider kernels where these are just like some like L infinity functions. And the shift operator of such a graphon is simply the Hilbert-Schmidt operator of the associated kernel. The cut norm of a kernel / graphon, which is the most important norm that is considered there, this somewhat asks what the largest difference between the actual edge density and a uniformly spread edge density is when just restricting to any two subsets of the nodes. And it turns out that this is actually equivalent to most operator norms of the shift operator for some intuition. These graphons can also be seen as random graph models in the sense that you can sample from them. So you would simply, for sampling, you would basically sample well, data from the unit interval, and then you would evaluate the graphon at these points, and then you can obtain like some weighted graph. And if you further sample simple edges, basically with respect to like some Bernoulli distributions on these weights, you can get a simple graph. So for these distributions, we would write HN and GN. And basically what we're saying here, for example, is that if W would just be a constant 1/2 function, this GN would just be Erdős-Rényi graphs. So this would just be the standard setup here. And so what I maybe also should have said that, well, one can also see any finite graph as a graphon by just like embedding its adjacency matrix as a step function. And the underlying assumption we have here, or like the modeling assumption, is that basically if we have like a certain graph, for example, this one, and we just replicate it any number of times, we would end up with the same represented graphon. For graph machine learning, however, what is very important is also the node features. So in many downstream tasks, the node features are actually just as important as the graph structure itself, or sometimes even more important. And in a recent work, also where the transferability and generalization of MPNNs was analyzed with graphons, this like notion of graphons has been extended to also accommodate signals. And we will also use, well, these results here. So this is like some slight simplification, but we take one-dimensional signals. So we have like as a signal space, we just have all bounded functions on the unit interval, which are like have values in some finite interval, basically. And so for the graphon signal space, we would simply consider tuples of like a graphon and the signal, and we define its signal cut norm, and also the graphon signal cut norm simply as a sum. So maybe one remark, the signal cut norm is just the L1 norm of the signal. And it is also possible to just sample from a graphon signal in the same way as you would sample from a graphon, just that, well, you wouldn't, if you have like sampled from something weighted basically from the signal, you wouldn't sample further. So here, this is, yeah. Okay. So one important modeling assumption is usually that we, well, the order of the nodes in our representation doesn't matter. And so if we want to develop a distance on graphon signals, it is also important that this is invariant with respect to relabelings of the unit interval. And we do this here in a slightly more general setting as it was done in this original work, where we take any smooth and invariant norm on the signal and the well, graphon space. And then you would simply form the infimum over all relabelings of the unit interval. In this case, like formally, these are just measure preserving bijections. And you would just basically apply them to the graphon and to the signal. What we're mostly interested in here are this like LP norms and the cut norm. And well, if we look at delta 1, which would be derived from the L1 distance, we would get something that is very closely related to the edit distance. So the edit distance for graphs is often used also in these types of analyses, and it's basically you take some graphs and you have like a certain number of operations where you just like well, kind of add one edge, remove one edge, and like all these kinds of things. And what one does now is one identifies graphon signals of distance 0. So we have this distance here, and this is only a pseudo metric, but we say like if this is 0, and this is actually the same for like all of these LP distances and the cut distance, then these graphon signals are weakly isomorphic, and by kind of identifying these, we obtain a proper metric space. And well, one very important point here that was made in this work is that also for the graphon signal space, in the same way as for the graphon space, this is actually compact. And an important point here is that this does not hold for any of these delta P metrics. These induce a strictly finer topology. This compactness that is proven using a version of the similarity weak regularity lemma and is extremely useful for the whole theory of graph limits. It is a very basic property that allows one to say, like, if you have any sequence of graphs, just you can take a convergent subsequence, or the set of all finite graphs is basically dense in this graph limit space. Also, in extremal graph theory, you can prove, like, obviously, like existence of some certain minimizers of the functionals you would have. And for GNN theory, what has also been done with this compactness is that people use it to prove some types of generalization bounds. Okay, besides that, there's also a graphon signal sampling lemma, where one can bound the difference in cut distance between a graphon signal and its sampled version by something that goes to 0 in the size of the sampled graphon signal. Okay. We've seen before that this notion of homomorphism expressivity can be very useful for well, judging the expressivity of some type of GNN model. And we want something like that in the graphon signal space as well. So we want ideally simple functions to compare different graphon versions of higher order GNNs. And for that, one can use homomorphism densities. So homomorphism densities are like homomorphism counts, just properly normalized to like the graphon. And these should ideally characterize weak isomorphism, similar to Lavache's theorem. They should characterize convergence with respect to the cut norm, and they should also characterize the KWL test. And the definition we make here is that, well, we basically couple the graphon values with the signal values. And what is important to note here is that for the pattern, we consider a multi-graph. So any edge in this pattern graph can have multiple, can occur multiple times. So we have a multi-set of edges. So basically in this product, any edge can also occur more than once. And so basically everything that is black here is the standard definition from graphon theory. But what we do here is we also add this additional term to accommodate for the signal. And it is important to here not only consider the signal itself, but also like continuous functions in the signal space acting on it. And these, well, functions here, we call them signal-weighted homomorphism densities. Some basic properties about these signal-weighted homomorphism densities, I put the definition here again. First is a counting lemma, similar to the standard case. So if f is just a simple graph, then basically this function here is Lipschitz continuous in the cut distance. Also, they characterize weak isomorphism in the sense that, well, the cut distance being 0, all delta p distances being 0, the homomorphism densities for simple and multigraphs being the same, and also the distributions of the random graphs sampled from such an object being the same. So all these things are equivalent. And the point here is also that these homomorphism densities are, if we compare it, for example, to just like a real random vector where you'd consider moments or something to say something about the distribution, these are somewhat analogous to moments for random graphs. And in this case, random no-featured graphs. Okay, so one additional thing I've mentioned before is that we want them to align with the KWL test for graphon signals. And the 1WL and KWL tests have been recently generalized to graphons. The formulation is just a bit more complicated than in the discrete case, mainly because we don't have a discrete node set. And so also the space of KWL colors or 1WL colors is infinite and not countable. And we actually also, like one would need a proper topological structure on that. And the KWL test for graphons can also be fairly straightforwardly generalized to graphon signals. Simply, so you would here just define the space that these colors live in that the test would choose. And then you can define a color refinement that works pretty similar to the discrete case, where you would start off with these atomic types here. So you take like the graphon values, you take the signal values, and then you update iteratively. But the multiset operation is just now like some push forward with respect to the Lebesgue measure. And then you have basically also just a function that maps, all tuples of nodes into a, KWL color space. And the output of the test is then the distribution of all of these colors, which is just a probability measure on the space of KWL colors. And just for the topologies, like everything is like pretty standardly chosen here. So the product topology and the weak topology on probability measures. And the point here for the signal-weighted homomorphism densities is actually that they perfectly characterize the KWL test. So for two graphon signals, the KWL test outputs the same distribution if and only if all of the signal-weighted homomorphism densities are the same now for all multigraphs F of tree width bounded by k-1 and for all possible exponents that we consider for the signal. And this is, rather involved, but one can also argue with the tree decomposition and basically build this gradually up. Okay, so now we have seen this metric space that we want to lift these higher order GNNs to. Now we just have to actually do it. And so we will start with IGNs as some sort of like an exemplary architecture to generalize them to the graphon signal space. And the building blocks are now not linear equivariant layers with respect to this discrete node set, but just bounded linear operators on kind of like these tensor products of the unit interval, which are equivariant with respect to all measure-preserving transformations of the unit interval. And the theorem here is that one can also characterize the dimension of these linear equivariant layers in a similar way as one would for the discrete case. The only difference here is that we obtain a smaller space, which basically is due to the fact that we work now with an atomless probability space. So considering any kinds of diagonals and these kinds of things doesn't really make sense, as these are null sets in Lebesgue measure. And actually, if you take like this viewpoint of the partition algebras, this is actually just the dimension of the Rook subalgebra of the standard partition algebra. And the way we build these invariant graphon networks now is just like exactly the same as we did for the IGNs in the discrete case, but simply replace every occurrence of the discrete linear equivariant layers with the continuous ones. And then you can also parameterize them with respect to the spaces we have here. And the canonical basis can also be seen just as a subset of the discrete one, where you just have like the operators that do not depend on any kind of diagonal. Just a quick remark about the asymptotic dimension of the discrete and the continuous one. This is not the primary motivation of this, because I mean, one could also try to find smaller bases of these kinds of spaces, but just like a very brief comparison. So if any of the output and input and output order are bounded, then in the continuous case, we are much smaller. We're actually polynomially, while in the discrete case, it would be super exponentially. And with similar growth, it's just a quadratic difference up to like some terms that would be exponential in K and L. However, one should say that usually one would care about rather small values of this like K and L, and for these one can see a well strict improvement, I would say, of the continuous version over the discrete one. Okay, so for these IWNs, invariant graphon networks, we can now study their continuity with respect to the, well, kind of graphon signal metrics we've seen before. And okay, so if we have some Lipschitz continuous nonlinearity that we use within the IWN, then the well corresponding IWN will also be Lipschitz continuous with respect to all the distances that are derived from the LP distances. However, for basically any non-trivial IWN where we have a nonlinear activation, these well models are not continuous with respect to the cut distance. And well, this kind of stands in stark contrast to MPNNs. So MPNNs usually only depend on the shift operator of the graphon. We've seen this before. We just apply the well adjacency matrix to our node embeddings and do that iteratively. So these do not come with these limitations. And the way you can see this in practice is, I mean, you can, for example, just like sample some graphons here, and you can just look at, well, you can evaluate them on their limit, which would just be like a weighted graph, in this case, like something constant, and you can evaluate them on the samples. And for an MPNN, you would see a nice convergence. However, for like an IWN, you'd see this divergence here. For the expressivity of IWNs, it can be shown that these models align closely with the KWL test. In the sense that, or well, the way one can show that is that, well, any multi-graph signal-weighted homomorphism density can be approximated uniformly well on the entire graphon signal space by some IWN. And as we had the homomorphism expressivity of the KWL test, this also means that, well, all these IWNs of order K are KWL expressive. And all IWNs would determine a graphon signal. Of course, what one could do now via the Stone-Weierstrass theorem, just get like some universal approximation of any graph parameter on compact subsets of these like delta P spaces. However, the problem here is that, well, these spaces are usually, because this is not a compact space and not even a locally compact space, these are super small. And so what one would have to do is, for example, just consider something finite dimensional, where you would look at graphs of like bounded graph size. And this is actually what has been done in a lot of these prior works that studied universality of these higher order models. Just a quick remark, we have focused on the IWNs here, but one can also look at other higher order extensions of these GNNs to graphon signals. So one example would be a refinement-based graphon neural network, where we would just basically take the KWL test and make like all of these, well, computations. We would just like translate them into into a GNN. And so you just start also with the initial tuple embeddings via the atomic types, and then you perform the iterated updates using like the shared MLPs and like performing integrals over like the neighbors, or over like in this case over the slices instead of like a sum. And the interesting point here is that one can also take this measure theoretic view, where one can say, okay, the same model that one defines here, because it aligns so closely with the KWL test, can also just be defined on the space of KWL colors. So basically, I mean, if we have any model that is at most KWL expressive, in the discrete case, of course, we can just factorize it over the colors of the KWL space. But the important point here is we can also do this in a way such that it is continuous, and that it is also so we can basically factorize the model, and these two formulations, where you'd have like the standard formulation on the graphon signal space and the factorization over, like in this case, the space of distributions of KWL colors, these two would agree. Okay, so well, now we've seen how we can basically lift our GNN to the graph limit space, and we have looked at their continuity and expressivity. And what we now have to do is we have to answer the final question: what can be said about transferability? So what we have already seen is that these IWNs and KWNNs, they do not converge, in the sense that if we sample node-featured simple graphs, they would not converge to the underlying graphon signal. So you can also, this is also illustrated here in this figure. Basically, yeah, we've seen this before. And well, this is tightly connected to the KWL test because, well, this discontinuity arises when we consider the multi-graph homomorphism densities there. And basically, because we already capture the full distribution of the edge weights in the first step of the KWL test. And yeah, I've already also shed light on these compactness issues. So MPNNs operate just on the compact, well, metric space with respect to the cut distance. And then with that, it's pretty easy to just get like generalization bounds and also like nice behavior of these MPNNs, convergence, transferability, like worst case results. However, well, these spaces that our IWNs and KWNNs have operated in as of now are not compact. So it's like maybe a priori not really clear what one would do. And this could be seen as a disadvantage and, well, has been in some prior work. So maybe there's still something we can say about transferability. So transferability in this case would mean that as we sample basically just like two graphs from the same graph limit model, and the node sizes grow, then the outputs of our GNN would be roughly the same. So in graph limit theory, this is also very related to estimability of graph parameters. And as I mentioned, in MPNNs, one would simply just bound the difference between the finite sample and its limit, and then invoke the triangle inequality. For higher order GNNs, one cannot do that. And one could ask oneself, well, is it even possible? Because, well, if we look at the distances that most people work with on these models, for example, the edit distance, or in this case, delta 1 distance, if we, for example, just sample independent Erdős-Rényi graphs from them, then it's not even guaranteed that this would, even with respect to relabeling, that this would, well, converge to 0. However, one can actually pretty easily show that if we are in this like constrained part of, well, graphon signal parameters, where we are in the closure of the span of all, well, multi-graph signal weighted homomorphism densities, then we still have some sort of transferability. So basically up to like some positive, well, additional constant that could be made arbitrarily small if we sample two finite node featured graphs from such a graphon signal, we could basically bound the expectation of their difference in, well, something that goes to 0 as n and m go to infinity. And the proof idea is rather straightforward here. So one would just, if one has this graph parameter, one would approximate it as a linear combination of these multi-graph homomorphism densities, and one would simply remove parallel edges. So if we have a multi-graph, you have a multi-set of edges, and one can just like disregard all multiple occurrences of a certain edge. And the thing you would end up with is just basically a cut distance continuous parameter, which is also the same, which gives the same output on all finite graphs. Because, I mean, if you look at these multiplicities, basically the monomials have 0 and 1 as fixed points. And this assumption for transferability is fulfilled by IWNs and also by any graph parameter that would factorize over the KWL space in the same way that we've seen it for these refinement-based, well, graphon neural networks. And one can also, well, experimentally verify this with this toy experiment here. We have the same set of example graphons. And what we would look at now is just the, 90% prediction interval width of kind of the predictions that we get when we apply some fixed MPNN or IWN to samples from this certain graphon in this case. And then you see the behavior, at least like in the, k equals 2 case, is actually very similar. And in terms of topologies, one could consider on this space, one can actually have like this hierarchy in some sense, where on the one end, we have the topology of cut distance. There we have the cut distance. This is compact. Convergence is characterized by these simple signal-weighted homomorphism densities. And this is kind of like the right way in, some sense to look at the 1W-L test and MPNNs. On the other hand, this is what, has been worked with a lot in prior analyses. This is the topology of the edit distance, and you can't really say a lot there. However, there's something in between the topology of the WL measures, where you basically have convergence, which is determined by convergence of these multi-graph homomorphism densities. And this is relatively compact in the sense that you can embed it in this KWL color space, or the space of KWL distributions to be more exact. And one can formulate the KWL test and all these like graphon neural networks in that, and that makes like the analysis more feasible. If you compare this to existing work, so there has been a lot of work on transferability for MPNNs, mostly with graphons, a few also with like sparse graph limits. And they usually assume they have some additional assumptions on like the specific graphon, for example, like something topological in the sense that the graphon is continuous or smooth or piecewise continuous. And these additional assumptions also largely influence kind of the convergence rate you would get. And for higher order GNNs, the only prior work that considered them that also had like some additional assumptions and didn't make any statement about the transferability. So in our case, similar to this prior work of like the graphon signal space, we can show that without any additional assumptions on the graphon, we also have a worst case rate for transferability up to like a certain small additive constant. Okay, so to wrap it up, what have we done? We have extended some results for graphon theory to these graphon signals. For example, the KWL measures and distributions, and most importantly, also the signal-weighted homomorphism densities, which we used to talk about homomorphism expressivity in this space. We've developed IWNs as an extension of IGNs to the graphon signal space, and we've also looked at these refinement-based graphon neural networks. We've analyzed the expressivity and continuity of these higher order models with respect to the common graph distances. And we have seen that despite this inherent discontinuity of the higher order GNNs with respect to the cut distance, transferability is still possible in some sense. And it's like a worst case result. If you look at further directions, what one could do is one could try to develop a KWL distance based on these KWL distributions. So in the past, there has been, developed this tree movers distance for graphs. And so this could be fairly easily generalized. Also, it would be interesting to see quantitative transferability bounds under some realistic topological assumptions of the probability space we're working on. So currently, for a graphon, you just have the unit interval, but you only see it as a measure space and not as a topological space. So it could be basically any standard probability space. But it is very likely that under some realistic topological assumptions, one can also get better bounds for the transferability. And it would be interesting to compare these to MPNNs, especially also, for example, the dependence on the order of the model. Then one has to say that, well, dense graph limits, or okay, let's say sparse graphs are more prevalent in, well, real-world graph modeling and also for GNNs. And this comes with some further challenges, but it would also be interesting to see how like all of these things can be generalized there. And then one has to say that transferability itself has some inherent limitations, in the sense that is also a worst case result that basically holds for all functions that you would consider in your hypothesis class of GNNs. And to get something stronger that would maybe also align more with what you, well, kind of see in practice, you need to consider further inductive biases of like the whole algorithm. So through training, the data distribution, maybe it's not like supported on the whole space, but on something smaller, and also the specific task you're trying to learn. Okay, so this was it so far from my side. I thank you very much for your attention, and yeah, if you have any questions, feel free to ask.